All right, today we're jumping into a really brilliant piece of mathematical wizardry. I mean, it's basically a powerful shortcut for understanding the very building blocks of our world. It's called the Hall-Rees cubature method, and believe me, it's changing the game for how scientists figure out the nature of molecules.
So let's just kick things off with the big question. How do we actually calculate the properties of a molecule? How can scientists predict how it's going to behave, or what its energy is, or how it'll react with other things? This is, no joke, one of the most fundamental challenges in all of chemistry. Okay, so here's our roadmap. First, we're going to look at why this is such a tough problem to begin with. Then, we'll get into this awesome shortcut called cubature. We'll see how it goes from just one atom to a whole molecule, and we'll even get to see what these things look like. After that, we'll touch on the proof that this whole thing actually works, and we'll wrap up by looking at what's next for this big idea.
All right, first up, the molecular calculation problem. Let's really get a handle on why trying to simulate molecules is just so incredibly hard.
The old way of doing this was, well, frankly, it was a mess. Imagine trying to figure out a molecule's properties. Scientists had to literally slice up the space around it into these complicated overlapping zones, one for each atom. And then, somehow, they had to stitch all those separate calculations back together. I mean, you can just imagine, the whole process is super clumsy and takes a ton of computer power. So this is where a much more elegant solution comes in. Instead of trying to calculate everything everywhere, what if you could just find a small, perfectly chosen set of points that gives you the exact same answer, but with way, way less work? Well, that's the core idea behind this shortcut called cubature. So what is cubature exactly? Okay, think of it like this. Say you want to find the average height of a massive crowd of people. You could measure every single person, or you could just find a few perfectly representative people, measure only them, apply the right weight to each measurement, and boom, you get the exact same average. Cubature is basically that, but for molecules. It replaces this huge, complex problem with a simple, weighted sum at just a few very special points. So, how in the world do they find these magic points? Well, it's this really clever four-step procedure. First, you start by describing the atom with a set of mathematical functions. Then, you use those to create these special operators for the x, y, and z coordinates. Now, step 3. This is really the heart of the whole thing. It uses a bit of linear algebra to find something called eigenvalues and eigenvectors. And look, we're not going to get totally lost in the math here, but what's so brilliant is that the solution to this step automatically gives you everything you need for step 4. The eigenvalues, they become the exact locations of your points, and the eigenvectors, they give you the perfect weights. It's just an incredibly elegant way to get the right answer.
Okay, so that's great for a single atom, right? But molecules are made of many atoms, so the big question is, how does this scale up? And this right here is where the true breakthrough of the Hall-Rees method really shines. And this really shows you the difference perfectly. You've got the old way with all that messy partitioning we talked about, but the new way, it's a total game changer. Instead of dividing up space, you just generate one of these special grids for each atom on its own, and then you just combine them. That's it. Seriously. No complicated divisions, no clumsy stitching together, just simple.
And this quote from the paper just nails it. The molecular cubature grid is defined simply as the union of all atomic nodes. You just figure out the special points for each atom and throw them all together into one big list. And that simplicity, that's exactly what makes this whole method so incredibly powerful.
Okay, so we've been talking a lot about these grids of points, but what do they actually look like? Let's dive in and finally visualize them.
So the simplest non-trivial version is this one, the 7-point cubature. This is kind of like the first level of the grid, and even this one gives you a pretty significant amount of accuracy.
And the geometry here is just beautifully simple. You've got one point right at the center at the origin, and then 6 other points placed perfectly along the x, y, and z axes. That's really the basic structure you need to capture an atom's fundamental 3D properties.
Okay, but what if you need more detail? To really boost the accuracy, you can move up to the next level, the 15-point cubature.
So this one includes those first 7 points we just saw, but it adds another layer. You get 8 new points, and they're placed right at the corners of a perfect cube that's surrounding the atom. This bigger, more complex geometry lets you calculate much more complex features of the molecule's electron density and do it precisely.
And the cool thing is, this method is totally scalable. If you need even higher fidelity, you can expand it again, this time to a 33-point cubature.
Now, the structure here is just really impressive. I mean, this is not just a random scattering of points. It's a precise architecture made of 5 distinct symmetric shells. You have the origin point, the axis shell, the edge shell, the face shell, and the cube shell. Each one of these layers is mathematically designed to capture more and more subtle features of the atom's properties with higher and higher precision. It's really elegant.
Okay, so this all looks super clever, right? But you might be wondering, is it just a really good approximation? And the answer is no. This method actually comes with a mathematical guarantee that it is exact. Let's see how.
The proof is laid out right here in what's called Theorem 1 in the paper, and it says that for a single atom, this method is not an approximation. It is exact for the whole set of mathematical functions it was designed for. So we're not talking about a close estimate here. This is a mathematical certainty.
And what's great is that guarantee extends from just single atoms to entire molecules. And on top of that, there's a second totally separate proof that shows the method is also the best possible fit in a statistical sense. That basically means it gets as close to the real true electron density as is mathematically possible. So you've got these two powerful independent arguments that prove this method is solid and correct. All right, so we've got this powerful, proven, and honestly really elegant method. So what does this mean for the future? Where could this take us? Not just in chemistry, but maybe even beyond.
Well, the next big frontier is tackling something called two-electron integrals. These calculations are absolutely essential for understanding chemical bonds, but they are notoriously difficult. The problem is, when two electrons get super close to each other, their repulsive force just skyrockets towards infinity, and all the math just breaks down. The big hope here is that this clever point-based approach, which, remember, avoids calculating everywhere, might just offer a new way to get around that problem.
You know, when you get right down to it, this whole thing just shows the power of a single, elegant idea. And it really makes you wonder, right? What other impossibly complex systems out there, in physics or finance or biology, are just waiting for someone to find the right mathematical shortcut to finally unlock them?